So when we were studying electrostatics, that time I had told you that if a charge is present, there's a space around a charge where the forces of attraction and repulsion. So these are called as electric fields, right? Now, if a magnet is present, there will be a space around this magnet too. Like if I have a magnet, fine, this is a magnet. So what happens is, whenever we have a magnet which is present, there are certain lines of space which are present around this magnet. And these lines form an area which is called as the magnetic field. So where you can experience the forces of attraction and repulsion of a charge, that was electric field. Where magnetic properties exist, that can be same. Attraction can also be present and repulsion can also be present. So attraction or repulsion. Fine, that is your magnetic field. So here, if I bring another magnet, sorry, not a charge. Suppose I have brought another magnet. In this region, I'll be able to experience either forces of attraction or forces of repulsion in this region, in this particular region. All right, so this is known as magnetic field. The entire concept of electric field, which we have studied, is now in terms of magnetic field. And this is an important conversion because we represent the magnetic field not by a letter M, by the letter B with a vector symbol on the top, because magnetic field is a vector quantity. So you'll use all the laws here. So B represents the magnetic field. SI unit is Tesla, represented by capital T, and CGS unit is Gauss, representing capital G. Representing this capital G. Now look class, one thing. When we are talking about this, here, I told you, just a second. Once we were discussing the electrostatics, that time I had told you that if you have electric charges present, so what we have? Coulomb as the SI unit, right? And that time I had told you that it's not necessary that you will be using electrostat unit or stat coulomb as the CGS unit, right? Because this is rarely asked. Now we'll be talking about coulombs in magnetic field. Tesla is the SI unit and CGS is the Gauss unit. But this Gauss is often used in the questions. Like I told you, that electrostat unit, ESU, this is not very important for you to remember. You should just remember Coulomb. And you must have experienced this too, that Coulomb is only asked everywhere. Whether it's millicoulomb, microcoulomb in the form of this, but you have Coulomb only. But in magnetic field, it is not like that. I have seen many questions where Gauss is also mentioned. So this conversion should be clear to you, that 1 Tesla is equal to 10 to the power 4 Gauss. All right. Now see, we are talking about magnetic field, magnetism and everything. And straight away we have started with magnetic field. One thing that I want to discuss about this magnet, whatever is this magnetism, what is the source of this magnetic field? Just a second. So about this, I want to discuss about this magnetism. So what exactly is this magnetism? Means, yes, we know magnets do exist, but can only magnet generate magnetism? So that I want to discuss first, basically about the sources of the magnetic field. And this is very important for your basics. See, you should be aware about what all things can produce a magnet. Now look here, class. First point is written as intrinsic electronic spin. In class 11th, you must have done that chapter. I think in structure of atom only. Have you done that intrinsic spin where m is equal to m or s is equal to minus half or plus half? S is equal to minus half and plus half for an electron, and you used to write everything, N, P, L, all the properties about it. Can you recall this from class 11's chemistry? Spin of electron minus half and plus half. Ever did or not?
No, ma'am.
Intrinsic
think
spin you have not done.
no, ma'am. For me, this was not there.
Okay, anyone else who has done this? Spin where minus half plus half we write about like 4p. If 4p is given, so first we write n as 4, then m, then L, then S. These 4 things, if one is given. You have not done this, any one of you, in chemistry? Other students apart from Yaya has given his answer. If this is mentioned, like 3p is mentioned, 3p square, so you write N, M, L, and this finally you write S. These 4 things about. Have you done or not?
Yes, ma'am. Yes.
Done?
Yes, ma'am.
Yaya, can you now recall? You must have done this. This is in the syllabus of chemistry.
Yes, ma'am. I now recall. Yeah.
है ना? You have done
Yes.
it. So there, this S, we just write it as minus half or plus half, whether it's minus half or plus half. So basically, what is that? Why I wanted you to recall was because when the electrons spin within the atom, whenever the electrons spin, so what happens? They spin either in clockwise direction or anti-clockwise direction in the atom whenever they spin. So that is written as minus half or plus half, just to show the directions. And when these electrons spin, they generate magnetism, magnetic fields. So that is one source. Second is, C class, we have totally studied about Coulomb's law. We have studied about the applications of Gauss theorem also, how a straight wire can generate electric field, and everything we have studied, right? But do we know that if a current carrying wire is present, can it do the reciprocal part? Can it generate the magnetic field instead of the electric field? Right? If a current carrying wire is present, a wire is having the electrons move, it is having the current present in the wire itself. But can this wire generate any field? So yes, this is very important, and we'll start our class with this only. There is a law, Biot-Savart's law. I think if the chapter is done in your school, you must have heard of it, Biot-Savart law. We'll start with this. So yes, if a current carrying wire is present, current carrying wire means a wire is present in which current is moving. This wire is present where current is flowing inside. So at a point, it can generate magnetic field. So this is a property of a current. Current carrying wire means a wire that can generate current. Okay, a wire which can generate current, which has current in itself. Then see, these were the indirect sources. Then straight away you have a bar magnet present. Bar magnet is a straight magnet, reddish or brownish color often, or blue color is also there. Straight wire which has now north and south polarity on the other side. And then we have this horseshoe magnet, like these inverted U. These kinds of magnets you must have seen. These are very heavy magnets. Bar magnets, these are lighter. But when we have these are heavy. These are heavy magnets. They have very high intensity and produce high intensity magnetic fields within them. Lastly, we have the sources of solenoid and toroid. Now, what is a solenoid? What is a toroid? Solenoid and toroid are there in your syllabus. So out of all these 4 sources, this one and this one, they both are present in your chapter. They both are available in your chapter, in your syllabus basically. So solenoid is what? We have studied that a current carrying wire produces magnetic field, right? If I turn the wire in the form of coils, this is called as a solenoid. And if I join the ends of this like this, if I join the ends of the wire like this and form it in the circle or make it in the form of a circle, it's called toroid. So here also, within them also, current will be flowing. Within them, current will be flowing like this, or current will come here, go here like this. Current also will be flowing here. And at points, it will also be generating magnetic field like this. So basically you have these many sources where you can generate magnetic field, where magnetic fields are generated, where the magnetic field is generated. Intrinsic electronic spin, current carrying wire, bar magnet, solenoid, and toroid. So all these things should be clear to you. Okay. Uh, who has joined? Soha. I think Soha is joined now. So why do you people join so late? All the introduction part and everything from the basics, these are being missed. Anyways, now write it down. It's a new chapter that we have started. Pay attention, all of you, because this is the beginning of magnetism. If you will not understand this and you will not be joining the classes properly, very few students are who are there completely regular in this batch. So at least join the classes properly. Write it down. This is the basics of magnetism, because once this is start, then till your EM wave, we'll not be discussing these basics of magnetic fields. Yes, text done once completed. This also. See, Mariam, Soha, Siddiqa. Okay. Yeah, now these were just the sources of magnetic field. When we were studying it, these were just the sources. So what all we have started with? It started with the magnetic field first, right? So it was the space around a magnet where its magnetic properties could be experienced. So we represent this just by the symbol B. SI unit is Tesla over here, and the CGS unit over here is Gauss. This conversion is very important. 1 Tesla is equal to 10 to the power 4 Gauss. And when we are discussing about the sources, intrinsic electronic spin is important, current carrying wire is important. Then you have the bar magnet, horseshoe magnets, means all the types of magnets which are available. And it's not necessary that you can have only a single type of magnet which is present. Any magnet which is available, which can produce the magnetic field, then you can. And lastly, we have the solenoids and the toroids. Now see, as I've told you, these two are only there in your syllabus, which we have to discuss. So I'll start with the first one. That is the case of current carrying wire, which I've already told you that this is known as the Biot-Savart's law. So when we are discussing this law, basically you have a straight wire which is present. Fine. So current is going through the straight wire. This is a wire which is having the current going inside it. So all the symbols are already written on the right hand side, whatever is the meaning of each. So I over here, this is representing the current flowing through the wire. So this is the straight wire. You have the current which is moving. Now see, R and DL. There's a slight difference between R vector and the vector DL when we consider it. See, this entire is the wire. Now, if I am taking a portion out of it, this DL, it is known as the current element, which has been mentioned over this side, that DL is the current element. This is the current element present, right? So this is DL. DL means we have chosen a segment from the entire wire is present, and it's very difficult to integrate the entire wire all the time. So what do? We just take a small portion from the wire and then we analyze whatever is the current that is flowing through it. So entire wire we'll not be considering. It's difficult to consider the entire wire firstly. Secondly, we'll just take a shorter portion from the wire. Okay, so if this wire is only known as current element. So it does not mean that this is the part of a current. It's a part of wire itself. Means when we'll take the unit, it will be having the unit as meters because it's length only. The way we take and measure the general and entire length of a wire, this will be just a segment from it. Now, this was current element, but you have one more vector quantity, which is the position vector. So here you have to analyze one more point, which we take. Suppose I have taken a point over here, which is point P. Now I'll take the separation from the wire to this point P. This is known as the position vector. Fine. Position vector basically means that separation of current to the point of calculation. All right, separation of the current. Or let me just tilt it. Let me just tilt it slightly so that it is visible. I'll erase this portion. Now see, we have this point over here, P. and this is the wire. So I'm joining it. Now look, this is our, so there's an angle between DL, this is the current element, this is the position vector. So this angle, I'm taking as it as theta, which is the angle between DL and the position vector R. I is the current flowing through the wire, DL is the current element, R is the position vector, and theta is the angle between the DL and the R. Fine. So this is what is our figure. Now, here you do not have any derivation regarding this. Straight away, we'll be seeing on what basis all these magnetic field which is generated at the point depends on. Now, there are 4 factors. According to this Parets-Servot's law, 4 points you have to remember. Fine. One is that this is directly proportional to the amount of current which is flowing through the wire. So dB means a shorter segment from the magnetic field we have chosen. That is, this magnetic field is directly proportional to the current. So dB is directly proportional to this current which is flowing. All right. Secondly, we've talked about this current element. So dB is directly proportional to DL also, which is current element, but it is actually the length of the wire. So this is current element. So current element. And see, class 1 angle we have written over here, which is angle between DL and R. So this, see, trigonometry, you all know. So sine of this theta, what is formed? dB is directly proportional to this sine theta. So this dB is directly proportional to this sine theta which is present. All right, so dB is directly proportional to this sine theta. All right, sine of angle which is present. Right? Now, lastly, the way in Coulomb's law we had seen the inverse square rule. Here also the inverse square rule is applicable. Whatever is the position vector that we have chosen, what was the position vector? It was R. So here this is inversely proportional to the square of R. So basically we say it follows the inverse square rule. This follows the inverse square rule. All right, so dB is directly, so 4 points, I'm repeating. 4 points. Once you have dB is directly proportional to the current. Secondly, we have dB directly proportional to current element. Third, dB is directly proportional to sine theta. Fourth, dB is inversely proportional to the square of the separation, which is the position vector. So 4 points we have over here. Now, look. So dB is proportional to all of these. So if I combine and write, what should I get? See, dB is directly proportional to I dl sine theta by r squared. So here also we'll get a constant. dB is equal to constant I dl sine theta divided by r squared. So the value of constant that we write over here, this is mu naught by 4 pi. This I'll tell in detail about the constant. Just write down the way in Coulomb's law we have F is equal to K Q1 Q2 by R squared. Here also we'll be having the same thing. It's just that the constants are different. Here we have mu naught, there we had epsilon naught. So this is the difference that comes. Epsilon naught, that was permittivity. Mu naught is permeability. There's a difference. But I'll be coming into the details of this first. First, you have the proportionality written first. Then I'll come to the media, what all media can influence it, and what is the difference between the permeability which is present over here and the permittivity which we had already seen in the first. So mu naught by 4 pi is the constant here, which is I dl sine theta. And here we have r square present. Fine. So here this will give you the magnitude of the magnetic field. Tell me. Till here, is it clear to all of you?
Yes, ma'am.
Others?
Yes, ma'am.
Okay, what about Sidra? Sidra, you have not answered anything. You have not responded in the class. Sidra, just check the mic. I think you are not audible. You have unmuted yourself though. I think you
Yes,
can
ma'am.
text in the chat column because your voice is not coming. Text me, that is better. I'll see your text chat box is already open. So I'll see. And Rishita, you too, respond please. You've understood till here. Okay. Write it down from this, then I'll discuss further things. First, write down this law. Okay, okay, okay.
Ma'am, 1 minute, can you go up? Done, ma'am.
Yes, completed.
Yes, ma'am.
Yeah. See, when we are discussing about the differences between the permeability and permeability, then we talk about, see, in when we are talking about electrostatics, that time it was in reference with the electric permittivity, means the medium on the force, dependency of the medium on the force which was present. Now, when we are talking about permeability, it means same thing which we are discussing in terms of the magnetic field which is present. Fine. So basically, this tells about the effect of the medium on the magnetic field. Now, you see here when we're talking about the constant term here, it was a simple dielectric constant which we were discussing. And the value which we were discussing was, what was the value of the constant dielectric constant K? Yes, class. What was the value? The Coulomb's law when you used to write. Yes, yes, yeah, yeah.
Can you repeat the question again, ma'am?
We have the dielectric constant when we were discussing electrostatics. K. What was the value of K? Hmm? Yes. F is equal to K Q1 Q2 by R square. What was this value of this K which we had? What was the value of this K? Yes, class. Now we are in magnetism. This we had seen in electrostatics itself. K. F is equal to K Q1 Q2 by R square. So this K constant, what was the value of
4,
this?
4 by pi 4 by pi epsilon naught.
1 over 4 pi epsilon naught. Yeah, that was the formula. But once you will insert all the values, what will we get? See, this is not how it goes. You have to answer. Firstly, this was done in electrostatics, and it's a value which I've told you, which you'll be utilizing everywhere. Electric field, if you're calculating, potential, if you're calculating the electric force. How can you forget the value? When we are writing this, F is equal to K Q1 Q2 by R square. This term, what do you substitute in the formula? You have to substitute a value.
9 into
Exactly. 9
10
into
to the
10 to the power 9.
power
Why
9.
was there such a big confusion and other students were not able to answer? This is not how it goes about. Yeah, this is 9 into 10 to the power 9. So see, when we are calculating the effect on a medium on magnetic field, here also the same thing will occur. Epsilon naught we had calculated, and yes, what was the value of this epsilon naught also in air? Okay, K you've told me 9 into 10 to the power 9. What was the value of this epsilon naught? Means the permittivity in air, specifically in this medium air. What was the value? Yeah.
8.5
Yes. Yeah. Correct.
into 10 raised
8.5
power.
into 10 to the power minus 12. This is the value which you should remember. Who has left? Yeah, Mariam Lohani has. As soon as I start asking questions, you people start leaving one. And when this session is over, then you join. See, 9 into 10 to the power 9 is the value of this constant K. And for epsilon naught, we have 8.85 into 10 to the power minus 12. Now coming to the constant over here in magnetic field. The value of this constant mu naught, which is the permeability over here, this value is 4 pi into 10 to the power minus 7. So in the constant of the Biot-Savart's law, we have the constant as mu naught by 4 pi, right? This is mu naught by 4 pi. So if you have mu naught by 4 pi, so now this constant, what do you think from this? If 4 pi comes in the denominator and it gets divided, then we are just left with 10 to the power minus 7. So if mu naught by 4 pi, the value will be just 10 to the power minus 7, which is the constant we'll be using. And same Tesla meter per ampere, same thing, same unit, but the value will be different. So in the same formula, B is equal to mu naught by 4 pi I dA sine theta by r square. Here, instead of this constant, you are going to use 10 to the power minus 7, the way you have been using 9 into 10 to the power 9 for the electrostatics portion of dielectric constant. All right. Now, if you have a different medium, which you're not aware of, and you've got this thing. So same thing, the way we have been using epsilon here, we'll be using epsilon. We used to multiply it, right, with k epsilon naught times for a medium. So here we just use C, mu for any other medium divided by mu naught gives mu R, means relative permeability. Relative means one medium with respect to another medium. Fine. So this is showing the relative permeability of the medium. All right. This tells about the relative permeability of the medium. Now, we'll be seeing this in the next chapter about the magnetic materials which are present, like you have ferromagnetic materials, diamagnetic, antiferro, all these materials are present. So all the materials which you have to study, they'll be having this ratio of the relative permeability in terms of 1. Like ferromagnetic substances, these are very much greater than 1. Mu r, this is approximately 1000. And then you have diamagnetic substances which have the value of 1, which have the value less than 1. Fine. So no, you don't need to remember it here. In the next chapter, I'll share a table with you where you can study it from here. Now, one more thing. If we're talking it in terms of vector form, so in vector form, you'll just multiply. See, when we are calculating the vector B, this is mu naught by 4 pi I dl cross r divided by r square. See, now this dl cross r means dl into r into sine theta. And here, just one thing, class. This is not r square. This will be r cube. Why it will be r cube? See, now here we have r in the numerator, because when you expand the cross product, for cross product, we take sine theta, right? dl r sine theta. So this r will cancel this cube. So then we'll get the actual formula which we were studying, which is r squared. Okay, write it till here, till the vector form. See, when we are discussing the direction of the magnetic field, firstly, you have to remember that this is perpendicular to DL and R. And secondly, we'll apply the right hand thumb. Now, here we'll see two methods for application of the right hand thumb rule. So, first method, let me discuss it. See, put your thumb, you have to keep your thumb. This is the current, you have to keep your thumb along the direction of the current. And then curl your fingers wherever the point is needed for the calculation. See, this is a wire, this is a straight wire having the current I. All right. So at this point A, if you have to calculate, so what you will do, put your thumb along the direction of current. Now here the current is going up, so you will keep your thumbs up. Thumbs up means that the nails should be upwards. The tips of the finger, the tips of the finger, these should be upwards. So you keep it parallel to the current wire, and then once it is parallel to the current wire, then you put the values, right? Okay. See here. If you look here, then you will see the fingers are coming out of this point, and the fingers are coming into this point. All right. So that's why we say A point is outwards, B is inwards. This I'll show you again in the next class too. Now, right now I'm just showing you the theoretical part. Next, I'll show you the practical also. So A point here, when you curl the fingers are coming out here. But when you put the fingers here, fingers are going inside. That's why you have the direction is outwards and inwards. Okay, that is the first method. This is the theoretical part written. First write it. Then you are going to tell me A, B, A, B. This is the first figure. This is the second figure. First A, first B, second A, second B. Whichever you have to answer, just mention it. Write it. See, in this part, this is similar to what the example which we have seen. If you keep your right hand thumb above, the fingers are coming outwards, right? And so here in this point B, fingers are going inwards. Now, when we're talking about the second one, thumb is pointing downwards. So, see, if the thumb point downwards, the finger goes here inside, which is inwards, and B, this is outwards. Fine. Just write it. And if you have any confusion regarding this, please let me know. Outwards, inwards. So I'll show you again and I'll tell you the method too also in the next class. But first write. Okay. Tell me and text me done once you have completed.